Hi, this is the third part for the instruction set architecture. And what we will do is we're going to discuss the branch and jump instruction. And the MIPS architecture makes a distinction between the branch, which is a jump plus a condition. We check on a condition, and the branch with the jump instruction, which has no condition to check, unconditional jump. Okay, so these are two branching. We have two branch instruction. BEQ branch, if equal, we check the equality of two registers, okay, RS and RT, and this could be T0, T1, S1, S0. And if they are equal, we jump to a label L1. Or branch if not equal, we check on the inequality of two registers, and if they are not equal, we jump into a label. Okay, so this is the condition that we check here. This is what the condition, the equality or not equality. Now, the important thing here is that that this jump instruction, the last one, there's no condition to be checked. Now, one thing important is that let's see if we get into a whiteboard here. Okay, so if I have branch if equal, whoops, sorry, a branch if equal. So I check on, say, for example, T0 and T1. Okay. Now, let's say I have a label. I'll call it L2. And this is a label called L2 here. Da, 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 da. So what happens is that if these are equal, then let's say I have here an add instruction, a subtraction instruction. After the branch if equal, the next instruction will be this one. Um, let's say that there is a load word, but if these are equal, I'm going to move the execution instead of here to L2. So L2 is a label, and anytime we say it's a label, it means it's an address. It is a label means, so this is an address. So how this address is stored in the machine language? Well, the way it is that we compute the delta between the current instruction and the destination instruction. That delta can be positive, or if the branching is backward, it can be negative. Okay, so let's say L2 might be here. And then we save off this delta into the machine code of the instruction. It's a 16-bit signed number, which moves me forward or backward in my code. Okay, so that's basically how we do it. So now let's see how we can implement if statement and loops using the branch if equal, the branch if not equal, and those jump instructions. Okay, so suppose, for example, I have this if statement that if I equals j, then I do something else, I do something else. Okay, so we need to check. Okay, so this can be anything. This can be one line, and then it can be, so I'll call this a y here, and y represent one statement or million statements, it doesn't matter. Or so if something is equal, do y, else if something is not equal, then do z. Okay, so how we can implement this in our MIPS instruction. So first, I'm going to assume that the I and the j, so the I is saved in S3 and j is saved in S4. So I'm going to check on S3 and S4 if they are not equal. If they are not equal, notice, then I'm going to jump into the else. Okay, so this is the else, which is the Z section. Okay, which is right here. Okay, the else. Now, what if they are equal? Well, if they are equal, I'm not going to jump, and I'm going to execute this part, okay, which I'm going to refer to it as the y. Again, z and y can be one statement or million statements. It's what I care about is the skeleton. Now, once I execute y, whether it's one statement or more, what do? I jump to exit statement. Okay, that now notice that else and exit are just labels. You can call it Charlie, B, L1, L. So these just names of labels. So they don't. So jump if exists. So notice jump unconditional because once I execute the Y, right, I don't want it to execute the else part again. So jump to the exit. And now if they are equal. No, so let's see if they are equal. What happens? And so oops. If they are equal, if they are equal, branch on not equality will not work. I am executing this so that if they are equal. Now, if they are not equal, well, I'm gonna jump to else, and here I'm gonna execute this if they are not equal. And I mean by not equal are those I and j, which is the what I want in an if statement. Now, what I could do here is that I can expand this notation of branching into implementing while loop. So in this while loop, what I want to do is I have a set of data here, all right, and this data, right, pointed to it or an array by save, and I want to count how many times I see certain value, and I'll call this value k. So do I have two of these values, four of these values, three of these? I want to know how many of these values I have. And to do this, we implement this. So we assume here that this save is this pointer is in S6, okay? And we assume as well that the I, right? The I, which is this index here, is saved in S3. Okay, all right, and the K, which I am comparing with, is um, is in S5. Now, if I want to explain or write what I want to do in C, it will be while save I equals K, increment I. Now, this will keep incrementing until I will find the very first instance where save I does not equal K. Then I will exit the loop. Notice here what I'm going to do first is that I will multiply the I by 4. Oh, but this is a shift left. Oh yeah, because shift left is an equivalent of multiplication. Shift right is an equivalent of division, right? Well, how is that? Well, consider for example, we have the value of 6. If I shift 6 to the left, it will be what? It will be 1100, which is 12. I multiplied 6 by 2 equals 12. Well, if I take 6 and I shift it to the right, it will be 0011, which is equal 3. I divide by 2. So any position, when you shift one position to the left, you are multiplying by 2. Well, how about if I shift left by 2 positions, we are multiplying by 4. And basically what we are doing, we are converting the integer index here into byte index. We say that the relationship that to convert integer index to byte index, you multiply by 4. So basically here what we are doing is that we're saying S3 times 4 gets T1 or saved in T1. And now I can access, I add the S6 here. Okay, so basically what we have is that we this is the index now. Now we add it to S6, which is the start of the array, which is the save here. Okay, so now we get the address of save I, okay, which is the start of the array plus the index here, okay, which is at T1. Now I can access the word, which is save I, and save it in T0 by load word. Then I can compare the word that I loaded from save I to S5, which is the K that I'm comparing against. Now, if they are not equal, I will exit. But if they are equal, I will increment the I, okay, and then jump to the loop and do the same loading and comparison again. until I find a mismatch where I exit the loop. Okay, so you can see how now I'm using branch if not equal and jump to construct this while loop. Okay, now, so this is basic blocks are referred to those blocks that they don't have jumps or branches. Okay, one of the concepts in very important for compilers as well. Now, what we have is we have an instruction that says set if less than. Set if less than means that I will compare two registers, RS and RT. If RS, if RS is less than RT, okay, then the destination register will be 1. Otherwise, it will be 0. Okay, so if RS is less than, well, that's why, see the name means what? Set the destination to 1 if less than, if this one is less than this one. Okay, otherwise RD is set to 0. Now, this data, the second data, can be either a register or it can be an immediate data. Okay, so for example, I can say here set if less than, let's see, destination register S0, compare for me T0 and T1. Okay, I could do that, or I can use immediate, S0, T0, okay, or and number 5. Okay, so this is the I means immediate data. The data is part of the instruction. Okay, now so here we can use set if less than and branch if equal to implement a branch if less than. What do we mean by branch if less than? Well, what if I want an instruction where I want to do branch if less than, I will compare two registers S1 and S2, right? And if S1 is less than S2, I want I want to branch to label L. Okay, so if S1 is less than S2, I want to branch to. Okay, so the question is this instruction part of MIPS? Answer, no, it is not part of MIPS. MIPS provide you the basic instructions to construct more complex instructions, because MIPS wants to keep number of instructions to a minimum to minimize the hardware, the cost, and to improve the speed of the microprocessor. Now, how can I achieve this? How can I achieve this? Well, very simple. The way you can achieve it by set if less than instruction followed by branch if not equal. So we compare S1 and S2. Now, if S1 is less than S2, T0 will be set to 1. Then we compare T0 to a 0. If they are not equal, because S1 is less than S2, then I branch to L1. Okay, then I branch to L. Okay, so let's say let's take the case, for example. Let me just go back here, and let's take the case where suppose S1 is less than S2. So if this is the case, then T0 will be equal to 1. Now, then we come here, we compare T0 to 0. They are not equal, then we will branch. So now, because S1 is less than S0, I was able to branch, which is the same as saying branch if less than, okay, S1, S2 to label 1. Okay. Now, what if let's assume that they are that S1 is greater than S2. What's going to happen? Well, what's going to happen here? Set if less than, this will be 0. Now, if when we compare T0 here to a 0, they will be equal. And because they are equal, we are not going to branch. Okay, so we will only branch if S1 is less than. So effectively, this is implementing this instruction, which is branch if less than S1 and S2 to L. This instruction is not in MIPS, but we can construct it using multiple instructions, exactly like the move instruction, exactly like the subtract immediate. Okay. All right, so this is saying we can expand to other one. Now, the set if less than can come with two flavors. It can come with set if less than and set if immediate. And in these two cases, we will deal with data as signed data. All right. Now we can deal with data as unsigned, only positive number. What is the difference? Well, the difference is the following. Take, for example, this number. If you take it as signed or unsigned, 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 this number is equal to 12. As signed, well, you have to get the 2's complement here, which is this one. So this becomes -4. Okay. So this is if it is signed, it is -4, and if it is unsigned, if it is it is 12. So now we have to tell the machine if I want to treat the data as unsigned. Take for example these two cases, this S0 and S1. We want to compare S0 to S1 using set if less than. In this case, S0 is a negative number. So S0 is less than S1. So we set T0 to a 1. Okay, so T0 is set to a 1. But what if I say, no, I want you to treat the data as unsigned? So in this case, S1 here, which is this one here, is a very large positive number. So is S0 less than? No, it is not. So we set T0 to T0 to $T0 to a 0. So this U informs the simulator that the data is unsigned to be treated. Okay. Now, in terms subroutines, let's go back. Let's go and look at one of the examples that I have for subroutine. It will simplify the subroutine a lot. Okay, and this is right here. Okay, let's see. Let's go back to the subroutine example. Okay, here is my example for subroutine. Okay, subroutine. My example for subroutine, basically here I have this is a program where we are calling. Okay, so this is a program, and I need to explain some of the structure for this program a little bit so that now you can notice here we have dot data. Dot data is where I define my data variables. So here I have two variables, data1 and data2. Now data1, I'm defining a word, that word. That means I'm defining 4-byte location and I'm initialize it to 5. And I have data2 as I'm defining it as a word, and this is 4-byte location and I'm initializing it to 10. Now notice I have here two programs. Dot text means I have a program. So this is data. This is now code program. Okay, and I have another dot text here, which is another program. Now obviously one of them is the main program and the other one is the subroutine. Now notice the subroutine. I know it's a subroutine because see how the skeleton for the subroutine, see how the skeleton, oops, see how the skeleton for subroutine, the name of subroutine dot, and then you can see here jump and return. Okay, now basically here what I'm doing here, I'm loading the effective address of data, whatever address for this data, I'm loading it into register A. So basically when I'm calling, now I want to call a subroutine here. Okay, and this subroutine I want to pass it certain input parameter. Typically we use register A, A0, A1 for that. Okay, and A1 for that. Now the return value, typically we send it back with V0 and V1. These are the return values from the subroutine. So we are going to add things here and send it back to now. So what I'm doing here, I'm loading the addresses for data into A0 and data2 into A1. Then I'm saying jump and link. This is how I call the subroutine. Jump and link, what it does, it transfers the execution. So see, jump and link my sub, it transfer the control here, meaning I'm calling the new subroutine. Now notice what I'm doing here. I'm loading the data in the address A0, which is data 1, okay, into T0, and I'm loading the address in A1, which is data 2, into T1. Then what I'm doing, I'm adding T1 and T0, and then I'm saving it off to V0. Now notice here, jump on register, meaning I will go to this address. What's this address? Well, you see, when I called here, when I called here, when I made this call, the return address is saved in return address register. So here, when I finish my subroutine, I say jump on this address, means I will come back all the way here. Okay, it will take me to the instruction right after the jump. Okay, now notice here, when I go back, I'll have the v0 with me with the correct value. Now I'm adding the 0 to a 0, and I'm saving it to t0. The whole program, what it does, okay, it will add this value of data 1 and data 2 and save it into t0. Okay, so but notice the mechanism of the jumps here. Jump and link, and jump on register RA. Register RA is a special register used for subroutines. Okay, special register used for sub. So this is the skeleton. This is the skeleton for a subroutine call. Okay, now let's go back here to where I stopped. Okay, so uh, okay. Now, one thing important when we call subroutine is that if so here, this is a subroutine, and which we can call with this name, right? Notice that last instruction, on jump register on RA. In the subroutine, inside it, I can change whatever T register I want, but I cannot modify the S registers, the S0 all the way to all of them. But what if I need to? If you need to, then you have to save the S register in the beginning of the subroutine to in a stack. Basically, we're doing a push. So this is a push to save it in the stack. And then at the end, we do a pop for its value. So basically, the effect is I'm saving the original value of S0 when I enter the subroutine, and when I leave the subroutine, I take its old value, so it appears that I did not change the S0. Now, the push instruction is that we subtract the stack pointer here, which is a special register, by 4, and then I write S0 to the stack. Okay, so the stack pointer is a special register which points to the top of the stack. I subtract, then I write. Now the pop instruction, basically, I write the whatever saved in the stack to the S0 to return its value. Then I increment the pointer here. So this is push pop instructions in the MIPS architecture. So notice here the stack pointer here is a special register here. The RA is the return register for subroutine. Okay, let me stop here and we'll continue the last section in the next lecture. Thank you.